Okay, before we go on to the next section, which is going to be taking our ratio test and root test and going hog wild with it, let's go back and just have a review of everything we've done so far and do a bunch of problems, okay? This is especially important to do with series. So let's begin with these three right here. Four of them, actually. Okay, these four really kind of capture all the ideas you need to know for series. So for each one of these, we need to determine, does it converge absolutely? Does it converge conditionally, or does it converge, or does it diverge? Remember, to converge absolutely means that we make everything positive and it still converges. Converging conditionally means that as long as there's some cancellation positive to negative, it's going to converge, but if you make everything positive, it will diverge. And then diverge means that even with the cancellation of positives and negatives, it still doesn't converge. Okay, so what about this one? This one here, if you were to write out the terms, you're going to get, if you start with 1, let's go ahead and make it like that. So it's going to be 1 minus the square root of 2 plus the square root of 3 minus the square root of 4. You see that those individual terms are getting bigger and bigger. In particular, those terms are not going to 0. And if the terms don't go to 0, boom, you can say this thing diverges. That's all there is to it. Okay, if the individual terms don't go to 0, the thing diverges. What about this one? This one here is going to be 1 minus 1 plus 1 minus 1 plus 1 minus 1. There too, they're not getting bigger, but they're not going to 0. That's all there is to it. It diverges. Okay? What about this one? The way to do the first thing to notice is that if you make all those things positive, you take the absolute value of all those things, it looks like this. Okay? And we know from what we've done already that this thing diverges, right? Because these things do not go to 0 fast enough. They don't go to 0 fast enough. It goes to 0, but not fast enough. This thing right here would look like what? Let's put this again. So it's going to be 1 minus 1 over square root of 2 plus 1 over square root of 3 minus 1 square root of 4, and so on. So they are not going to 0 fast enough. If you make them all positive, it would diverge. However, the fact that they are going to 0, and in fact, remember the theorem? These things are, without the negative 1, without the alternating sign, these things here are monotonically approaching 0. They're going to 0. Each one is less than the previous one. And so then we proved that if you have something like this, which is going to 0, it doesn't matter how fast, as long as it's going to 0, and as long as you alternate the signs, remember what happens? It looks like this. Start there, then here, then here, then here, then here, then here, then here, and it converges to something in between. So that thing does converge only on the condition that they are canceling the positives with the negatives. So this thing here converges conditionally. Okay? And finally, the last one, if you slap on absolute values for that, over n squared, this thing here, n plus 1, is going to be what? 1 minus 1 fourth plus 1 ninth minus 1 16th, and so on. You slap on absolute values. If you do, boom, boom, you're going to get what? 1 over n squared. Doesn't matter whether you have positives or negatives there at all. Those things go to 0 so fast that when you make everything positive, it still converges. It still converges. So this thing here converges absolutely. Okay? So those are basically the 4 ideas, and all you have to do then is just apply those to other series. Okay? So let's do a few over here first, and then we'll might as well just erase them. Then we'll start fresh. Okay, so all of these, you should turn off, pause the video and figure them out for yourself before I do it. If you just listen to me, you're not learning a thing, okay? Mathematics is not a spectator sport. You get a whole lot of people who think they know math just because they can shake their head yes when someone else explains it to them. You be honest with yourself. If you can't do it yourself, you don't know the problem, okay? So that's what I'm here for, to explain it to you, but you determine whether you know it. So let's do this one. How about -1 to the n, 2n plus 3 over 5n plus 7. Okay? Can you tell right away what that one does? That's the idea. Each one of these I'll write down. I think I'll be able to just say right off the bat. This one here, I'll tell you right now, it diverges. The reason it diverges is because these individual terms are approaching 2/3. Agreed? They're approaching 2/3. They're not going to 0, so this thing diverges. Okay? How about this one? What about that one? Well, again, I can just look at these, and here's the way I look at them. I say, well, if you slap on the absolute values, I'm just going to go like this. If you slap on the absolute values, here's what it looks like. That just looks like that's what it is. It's this. Oops, n. And this thing right here converges. Why does that converge? Because it basically acts like 2/5 to the n. It acts like 2/5 to the n, and that's the geometric series with anything less than 1 is the ratio, and it's going to converge. How do I prove it formally? I say I use the nth root of the nth term. And when you do that, these two ends cancel each other out. That limit there, as n goes to infinity, is equal to 2/5. 2/5 is less than 1 in size, and so this thing here converges. It converges, notice, without the use of the negatives. We didn't have to use that at all, so that converges absolutely. Okay, that's the way that one works. Let's try another one. How about this one? My machine just stopped, but I caught it right on time. So I was writing this one down, this one right there. So I think all I was saying was, notice that for this one, ln of 1 is equal to 0, so you'd have to start this one at 2. So I'm not writing them all down, but you start at whatever number is needed in order to not have things be 0 at the beginning, 1 over 0. So what about that one, okay? Again, you can do this one kind of in your head once you get to know them. First of all, notice that this thing is going to 0, right? Because this thing is getting bigger and bigger. And so 1 over that is getting smaller and smaller. So right away, because this is there, I know that either it's going to converge absolutely or it's going to converge conditionally. So all I have to do then is check this part out here. And how would you do that one? I look at that one and I say, oh, that looks kind of like this situation. Let's say from 2 to infinity, dx. And you go ahead and do that one, and you can let u be equal to the ln of x. du is equal to the ln. Is equal to 1 over x dx. And so this becomes just the becomes what? Becomes du. Let's see, doggone it. It becomes 1 over u du to infinity, and the antiderivative of that is the ln, so it's going to become the ln of the ln of x. So this is the ln of the ln of x by the time you're done, and you go off to infinity, and that thing is going to go to infinity very, very slowly. You put in, I think I mentioned this earlier on in the course, you put in as big a number as you can there, and by the time you take the ln of it, you're only at about 7 or something like that. So it grows very slowly, but that's the power of mathematics. We can still say it's going to infinity, even though our lifetime is a smidgen compared to the amount of time it takes that thing to get big. So the point is, since this thing goes to infinity, this one does too by the integral test. So, or I should say this one does. So that means it converges conditionally, right? Because these terms do go to 0, but they don't go to 0 fast enough to make it converge absolutely. Okay, let's do some other ones. How about, let's see, how about one like this? Let's see, how about, let's do n factorial squared over 2n factorial. Okay, let's try that one. Well, what's going to happen there? First of all, well, it's kind of hard to know whether these terms are even going to 0 or not. But when I see a bunch of factorials, I want to use the ratio test. So let's go ahead and use the ratio test on it. So here we go, n goes to infinity. What do? I take every place I see a n, I put an n plus 1, so it's going to be n plus 1 factorial, quantity squared, all over 2n plus 1. Be careful here, it's 2n plus 1 factorial. You got to be really careful there. See that? 2 times n plus 1 factorial, all divided by, so now I'm going to flip it over and get 2n factorial over n factorial squared. Okay, what happens when we clean the fish, as it were, get rid of most everything we can? Notice that this n factorial is going to cancel with all of these from n down to 1. All of those are going to divide out. All I'm going to be left with is an n plus 1. But I'm going to have it squared. So I'm going to get an n plus 1 squared right there. And now, what about this thing? Notice that this becomes 2n plus 2 factorial. See that? This thing right here, you got to be really careful, is 2n plus 2 factorial. What is that? That's 2n plus 2 times 2n plus 1 times 2n, boom. Well, as soon as you get to 2n, it cancels with all these. So those cancel with all these, but I'm left with those two right there. So I'm left with 2n plus 2 times 2n plus 1. See that? And now I look at this, and I say, what happens here? If I were to multiply out the top, I would have an n squared. If I multiply out the bottom, let's just write it like this. Multiply out the top, I'm going to get an n squared plus stuff. Multiply out the bottom, I'm going to get a 4n squared plus stuff, smaller stuff. And what's the point? The point is all these other things are insignificant compared to your n squared. That's the one that matters. And so this limit here, as n goes to infinity, is going to be 1/4. 1/4 is less than 1. So that means that this thing, I didn't need this. I took them all to be positive. I didn't need that, and I still showed that it converged. So this thing converges absolutely. Okay, converges absolutely. So so that's the idea. Okay. So with the root test and the ratio test, either it's going to converge absolutely, or else it's going to diverge. As I said, there's nothing subtle about that. Either they go to 0 really, really fast, or else they're not going to 0 at all. They're diverging. So there's nothing subtle when you use the ratio and the root test. Nothing that just barely goes Nothing like this. Okay, let's try something else. I don't know, let's get some ln's in here. How about this one? How about this one? How about ln of n over n, all negative 1 to the n. Okay, what about that one? Well, I look at that and I say n is growing faster than the ln of n. So the ln of n over n, that thing is going monotonically to 0. So the fact that I have this thing there means it's going to at least converge conditionally. Will it converge absolutely or not? Will it converge absolutely? In other words, if I get rid of that, will it converge? Hopefully you look at that and you say, no, it can't. Because I look at this and I say, hey, the ln of n over n is bigger than 1 over n. Agreed? As soon as n gets past e, this thing is going to be bigger than that. And what do I know about this? I know when you add all those together, that diverges. So that means by comparison, when you add all those together, it's going to diverge. Okay? So this one here converges only because of the fact that the terms are going to 0 fast enough. Okay? Let's try one a little more interesting. How about this one? This is where you just really need to understand your functions. If you, it's kind of like in finding antiderivatives. You just have to know them well enough to be able to say, I need to use the integration by parts on this, or whatever else. It's not like taking the derivative where you just start mechanically doing something. You have to see the answer before you begin. Okay? I have to know the answer to this one. I have to see it before I begin. And here's what I see. Okay? Here's what I see. I know that the ln of n grows slower than any power of n. I know that that grows slower than any power of n. Let's say n to the 1/4 power, which would be the same as the 4th root of n. Okay? I put that up on the board here several weeks ago now when we looked at comparative rates of things. Okay? So that's key. Okay? And I also know that this thing here is bigger than 1. And that's key, because if the p-test, if you have a power of n down there bigger than 1, it's gonna converge. Okay? That goes to 0 fast enough. So here's what I'm going to do. I'm going to start with this. And I'm going to say, given that this squared is less than or equal to this thing squared. If you square this, you're going to get just the square root of n. Okay? If you square this, you get the square root of n. And so now, if I take this thing, divided by n squared, that's going to be less than or equal to the square root of n over n squared. And the square root of n over n squared is 1 over n to the 3/2. See that? So here's the key. I know that this thing here converges. Right? This is bigger than that. That's a power of n bigger than 1. So this thing converges. These are all less than or equal to these, and so these are going to converge. So the point is, this converges fast enough. I didn't need this at all. These go to 0 fast enough that this is going to converge absolutely. Oops, I made a mistake here. Excuse me. This one here should have been conditionally. Okay, I hope you caught that one. That one converges conditionally. Okay, this one converges absolutely. Okay, very good. Let's try another one. You can just have lots of fun with these things. I don't know, let's do another one with the ln. How about 1 over the ln of n to the 5th power? What about that one? And again, I'll put this up on top here. Won't make it quite so messy looking. Okay, what about that one? Can you see that one just by looking at it? Can you tell just by looking at it? If you caught on to what I said in the last problem, you'll be able to. Because, again, I know that this thing grows slower than any power of n. So here's what I can say. First of all, I can say this. I can say that 1 over the ln of n to the 5th power, that thing monotonically goes to 0. When I say monotonically, I don't care if it happens to go up here right at the very beginning. The point is, once you get past a certain point, it's just decreasing. With all these problems, you're interested in the tail. A finite number of things at the beginning, you don't care if these things add up to 100 million. The point is this thing here is that going to be a finite number or an infinite number? Okay, that's the key. Looks like I got a banjo there, or a guitar rather. Okay, so the point is they do go to 0. Okay, so I know it converges at least conditionally. Does it converge absolutely or not? And I look at that. Okay, turn it off if you don't know the answer, because I'm going to tell you. Okay, this thing here doesn't go to 0 fast enough. Why do I know that? I know that the ln of n is less than, say, the 10th root, of n. So that means that the ln of n to the 5th power is less than this thing to the 5th power. And if you take this thing to the 5th power, it's n to the 1/10 all to the 5th, which is going to be the square root of n. Whole bunch of algebra there, okay? I'm not going to do it all. I'm mentioning it, but I'm assuming that anyone watching this stuff knows their basic algebra, okay? So you got that. Now, what's the reason for that? Because now I know that 1 over this is going to be greater than or equal to 1 over this. See that? These are less than, so if you flip them over, it's greater than. And what do I know about this? I know if you add all these up, they don't go to 0 fast enough. They go to 0, but not fast enough. So neither will these. So this thing here converges conditionally. Okay? So that's the idea. Okay? So you can just make them up just the way I'm making them up here. Okay? Let's try another one. Let's see. I'm going to have to erase some of these now. Okay? How about this one? How about this one? How about that one? Okay, that one, you look at that one, and again, if you don't know it, by this time you should know it. We've been doing this a few times already. You know that this thing right here goes to E. Okay, that thing goes to E. So this whole thing here is approaching E, and so it's just like adding and subtracting E as you go. So these things are diverging because the terms aren't going to 0. Okay, the terms are not going to 0. So there you go. Okay? How about this one? How about that? Well, here's what you can do here. You can take the limit as n goes to infinity of the nth root of the nth term. And so that's going to be this thing n squared all to the 1 over n. And so you multiply those, and that's going to be the limit as n goes to infinity of 1 plus 1 over n to the n, which is E. Here, we said it diverged because the terms are going to E. Here, we're going to say it diverges because it's the nth root of these things which is going to E. And in this particular, here, the important thing was that this thing is not equal to 0. That's why this thing diverges. This thing is not equal to 0. Here, we're using the nth root test, and so it's the fact that this e is greater than 1, which is why we say that this thing diverges. Okay? So that's why you really have to know what you're doing with these. You can't just kind of remember a whole bunch of rules. You'll get confused. You have to understand what's going on. With your root test and your ratio test, you're asking what's the ratio, or what's the limit of the nth term. Okay? So there's that one. What if we change this one to this? If you change it to that, I'll let you figure it out, but you can use L'Hopital's rule on that. And this thing right here is going to converge to 1 over e. It's e to the negative power, so it's going to be e to the negative 1. Okay? It's still not equal to 0, so this thing here would still diverge. If you had a negative in here, now you're going to have a negative here, and a negative here, and this is going to be a 1 over e. 1 over e is less than 1, so this thing is going to converge absolutely. Again, when you use the root test and the ratio test, you make no use of this at all. Okay? Either it diverges or it converges absolutely. Okay? So that one does that. Okay? Oh boy, you just go crazy with this stuff. Let's see. How about this one here? How about n factorial squared? I kind of like that one. Over n to the n times oh, I know. Yeah. Let's do this one. N factorial squared over n to the n. Okay, let's see what happens. And we'll throw a negative 1 to the n in front. Okay? So, use, whenever you see factorials, ratio test is the thing to do. So here we go. So, you're going to go what? N plus 1 factorial, quantity squared, all over n plus 1 to the n plus 1, agreed? All divided by, so that means I'm going to flip it over and multiply n to the n, all over n factorial quantity squared. Limit as n goes to infinity. Let's do the fishing stuff. Clean the fish. And let's see. One thing I can do with these is I can first of all take a n plus 1 out of the bottom. That takes care of this 1 right there. And then I'm left with n over n plus 1 to the n power. So I'm left with that. Then what do I have here? Notice that here I have n factorial, there I have n plus 1 factorial. So I'm going to have an n plus 1 remaining there, and I've got it squared, so it's going to be 2 of them like that. So that takes care of all this stuff. Okay? So now I'm pretty much done. Okay, what's this going to do? Limit as n goes to infinity. What happens? One of these cancels with one of these, and I'm left with an n plus 1 right there. This thing right here, notice, is the reciprocal of 1 over n plus 1 over n. See that? So I could write this thing all like this if I wanted to. Why would I want to write this like this? Because this thing right here I know goes to e, right? Because now it's 1 to the n over this thing to the n. And this thing right here goes to e because that's 1 plus 1 over n right there. Okay? So this goes to 1 over e. So you have that right there. Okay? This goes to 1 over e, all times n plus 1. N plus 1 times 1 over e, it doesn't matter. That's a constant. That's going to go off to infinity, which is bigger than 1. And so this thing diverges. Okay? Let me make Make sure that everyone is still watching me here. Okay, good. Everyone is? Okay. Let's see, how could we spice this one up so that it converges instead? I need to get another n downstairs there, don't I? How can I get another n? How about what if I do this to the 2n? What about that thing to the 2n? How's that going to affect things? Well, let's give it a try. Limit as n goes to infinity. Again, I'm leaving off the -1 to the n. Either this thing diverges or it converges absolutely. There's one or the other. So let's see, what do we do here? It's going to be n plus 1 factorial, quantity squared, all over n plus 1. And here, every place I see an n, I have to put an n plus 1. So let me do that in my head. I put an n plus 1 there, times 2 is going to be a 2n plus 2. See that? It's going to be a 2n plus 2 there. Now, flip it over and multiply n to the 2n all over what? All over what? N factorial squared. So what happens? These go with all of these, leaving just an n plus 1 quantity squared up on top, right? Because I have an n plus 1 for each one of those. Right here, notice I've got an extra 2n plus 1s there. So I've got an extra 2 of them right there. And then I'm left with n all over n plus 1 to the 2n. See that? I'm going to have n to the 2n over n plus 1 to the 2n. So, notice that all this just choom choom goes out, and all I'm interested in is this. What's that equal to? Well, I can write that as 1 over n plus 1 over n, quantities, I'll write that as to the n power, and then write this thing, quantity squared. See that? There's a guy who knows his algebra, okay? I know my algebra. I know that if you take 1 squared, it's 1. If you take this thing squared, it's going to be, you multiply the exponents, you're going to get a 2n there. So I'm going to get this thing, this over this to the 2n. Why do I want to write it like that? Because now it's going to be 1 over. This thing right here is all going to e. And so it's going to be 1 over e quantity squared. 1 over e quantity squared, which in particular is less than 1. And since that's less than 1, I know that this thing right here is going to converge absolutely. Okay? There you go. So if you really wanted to make it interesting, you could put like a 4 or 5 up here. You could have put a 5 to the n up there, and by the time you're all done, you're going to end up with a 5 right here, and now you compare a 5 with an e squared, and you check to see which of those is bigger, and either it's going to converge or diverge depending on whether you have a 5 there or an 8. If you have an 8 there, or a 9 for sure, it's going to diverge. With a 5, I think it's going to converge. Okay, so you play with those. Okay, so let's see how we're doing here. Yeah, that's a good bunch of them. Okay, so that's a good review of all the different things we've done thus far. So let's just try one more that comes to mind. I haven't done any trig functions yet. What about this one? What about that? Can you tell right away that that's going to converge absolutely? I don't have the negative 1 stuff in there, but the point is, if I slap these things on, the sign of anything is never any bigger than 1, right? This is never any bigger than 1. So this thing right here is less than or equal to 1 over n squared. And what do I know? I know that this thing right here converges absolutely. And these things here are all less than these. These are all non-negative, and so are these. And so since these are all non-negative and they're less than all these, and these things here converge absolutely, I know that this thing converges. And it converges with the absolute value, which means that this thing here converges absolutely. Because when I slap on the absolute value, it's equal to this, which is still less than this. And so since this thing converges, so does that. Since this thing converges, that means that this thing converges absolutely. Okay? How about, as long as we're playing with sines and cosines, how about this one? How about just this one? Cosine of 1 over n squared. What about that one? Converge or diverge? This one requires you know your trig functions. As n gets big, this thing goes to 0. The cosine of 0 is 1. So these things here are approaching 1, which is not equal to 0. This thing diverges. Boom! See that? You have to know everything. That's why this stuff is fun. It really forces you to know all the analysis, all your functions coming in. Okay? Let's do another one like this. How about this one? What about that one? As n gets big, this thing goes to 0. The sine is going to 0. Since this thing is going to 0, we don't know, right? The question is, how fast is it going to 0? How fast is it going to 0? Okay? How fast is it going to 0? Well, this is where, if you're really sharp, you'll say, hey, I remember that the sine of x over x as x goes to 0 is equal to 1. What this is really telling you is, without all this mathematical symbols, is it's saying for small things, the sine of that thing is very close to that thing. Okay? As that thing gets really, really small, the sine of it is essentially the same as the thing itself, which, look at the graph of the sine. Looks like this. Whoops, I didn't do that very well, but let me do that a little bit better. Here's y equal x, here's y equals sine of x. If you come in along close to the origin, those two things are indistinguishable. Graph them out on Decimus or on your calculator, you'll see they're indistinguishable. So when I look at this thing right here, I say this thing right here is basically acting just like 1 over n squared. For a small thing, this thing acts just like 1 over n squared. How do I prove it? Here's the way I prove it. I take the sine of 1 over n squared and I compare it with 1 over n squared. And I say what happens to that as n goes to infinity. And so how do I do that one? How do I do that one? I'm going to have to use, these things are both going to 0. I'm going to use L'Hopital's rule on it. In order to use L'Hopital's rule, I have to take the derivative, and for taking the derivative, I'm going to rewrite those as x's, because whatever the limit as x goes to infinity, n's going to do the same thing going to infinity, because n just takes on the integer values. So that's all fine. So now I can do this. Let's see once what happens. X goes to infinity. What's the derivative of the sine of anything? It's the cosine of that thing, right? Times the derivative of this thing. The derivative of that is going to be what? That's x to the minus 2. So it's going to be minus 2 x to the minus 3. So it's minus 2 x to the minus 3. So it looks like that. Down here, look at here, the same thing. Negative 2 x to the minus 3, so let's be there. Boom, boom, those two go away as x goes to infinity. This thing goes to 0. The cosine of 0 is 1. What's the importance of this 1? Okay, it's very different from the importance of 1 when you're doing the ratio test or something. What's the importance of this 1? This 1 is important because it's saying that this function here and this function here are growing at about the same rate. They're indistinguishable from each other. And what do I know? I know that since this thing converges, I know that this thing is going to converge. So this converges absolutely. My phone is ringing. That's it. Hey everyone. I just realized after getting the phone that there were 4 more problems that I wanted to do just to kind of finish out all the things I wanted to say by way of review. So let's do them. I've got them written up here. And I won't go through all the details of each one, but again, these are ones that if you really understood this stuff, you'd be able to look at each one of those and tell me instantly whether they converge absolutely, converge conditionally, or diverge. Okay? So let's take each one in turn. This first one here, 2n plus 7 over the square root of 5n to the 5th plus 3n squared plus 8. So the key here is that you've got, what do you have? You have a 2n on top. You have a square root of 5n to the 5th right there, which acts like 2n over square root of 5n to the 5 halves, which acts like 2 over square root of 5n to the 3 halves. See that? So this thing right here really acts like this constant doesn't matter. Who cares about the constant? You can pull that out front. But you have a 1 over n to the 3 halves. And what do we know about the series 1 over n to the 3 halves? The series, not the sequence, but the series. We know that this series converges, right? Because 3 halves is bigger than 1. It grows fast enough, so that thing converges. And since this thing converges, this thing acts like this one, and so it's going to converge. So the way you would actually prove it is by taking these things right here, 2n plus 7 over this whole thing right here, 5n to the 5th plus 3n squared plus 8, and then you compare that with 1 over n to the 3 halves. And so now you just flip this up and you divide both the top and the bottom by n to the 5 halves, and you're going to get 2 over the square root of 5. What's important about the square root of 2 over square root of 5? It's just a number. It's a number between 1 and infinity. That's what's important about that. And so the point is that means these things act just like these. And when you add up all these things, it's finite. And so when you add up all those things, it's finite. Okay? That's the idea. That's the limit comparison test. I think that's probably I think the single most important test in all of well, maybe with a ratio test, because it really gets to the heart. Do you really understand what these things are doing? Okay, so there's that one. This one is same idea, right? All you have is a n cubed down there. So now this becomes an n cubed, and so by the time you're all done, that's going to act like 1 over n to the 1/2 power. Okay, look, n over n to the 3 halves is the same as n to the 1/2. What do we know about this series? We know that that series diverges. And so since this one diverges, so will this one, because they act the same. They basically grow at the same rate. So this thing, without this, it's going to diverge. The terms don't go to 0 fast enough. However, these things do go to 0, right? Because the bottom is getting big faster than the top. So they go to 0. And so this thing here converges absolutely. This one converges conditionally. Okay? What about the next one? The next one, look at there. That's going to just act. That thing right there is just going to approach 2 over the square root of 5, right? Multiply the top and the bottom by 1 over n, and you bring it in. That means that these individual terms are not going to 0. Since they're not going to 0, this thing diverges. See that? So there you go. And finally this one. Now you have a 2 over square root of 5. So you have something like this, but now you're taking it to the nth power. So if you take 2/3, that thing is going to diverge, but if you take 2/3 to the nth power, that's a geometric series. That converges because r is less than 1. Similarly here, if you use the root test on this, what does the root test say? It says I take the nth root of this thing right there, which by the time you do both of those, you're just going to get the insides out. Okay, back to fission again. It's going to be 2n plus 7 over square root of 5n squared plus 3n plus 8. And that limit goes to 2 over square root of 5. What's important about this number? Now you've just used the root test, so now what's important is that's less than 1. Since that's less than 1, this thing converges absolutely. So there you go. So all these problems, that's a good review of all these things that we've been learning over the last several days. Very good.